Hello and welcome again to the channel. So this is a tutorial on Tornado development environment for Vxworks. As per request, we are getting into the in a sequence. So this is how the Tornado IDE for Vxworks looks like. So before getting into that Tornado IDE for Vxworks, this stuff is purely for beginners in a systematic way of learning the Vxworks. So I'll give you a brief introduction how we go about the tutorials. So initially we will in this video we will see about Tornado IDE. Later on into the Vxworks we'll look into the tasks and then inter-task synchronization, task communication, basic IOs, interrupts and timer, and then POSIX, and then shared memory, signals, configurations. So coming to the programming, we will implement and see in Vxworks like timing, multitasking, semaphores, message queues, round robin task scheduling, preemptive, priority based task scheduling, priority inversion, signals, ISRs, that is interrupt service routines, and then implementation of various other things in the programs. That would be the and so that you will have an idea about you will for this is purely for beginners and below average or at an average aspirants. For average aspirants, genius people can ignore this. To the best of my knowledge, I'm using best possible figures or best possible pictures used in it. Please kindly bear with a few of the pictures which I might have taken a little blurred or anything. So, getting into the Tornado. Tornado is an integrated environment for software cross development. It provides an efficient way to develop real-time and embedded applications with minimal instructions on the target system. Tornado compromises the following elements like Vxworks, a high performance real-time operating system, application building tools, compilers and associated programs. An integrated development environment IDE that facilitates managing and building projects, establishing and managing host target communications, and running debugging and monitoring Vxworks applications. So key features of Tornado are an integrated source code editor, a project management facility, integrated C and C++ compilers, and make it the browser, which is a collection of visualization aids to monitor the target system. Then Crosswind, which is graphically enhanced source level debugger, and WindSH, a C language command shell that controls the target. An integrated version of this Vxworks target simulator named VxSim. An integrated version of WindView software logic analyzer for the target simulator, and many customization options for many features. The Tornado environment is designed to provide this full range of features regardless of whether the target is resource rich or resource constrained. Tornado facilitates execute primarily on a host system with sharing access to a host based dynamic linker and symbol table for a remote target system. Illustrates the relationship between the principal interactive host components of the Tornado and target system. So this is how it illustrates communication between the host tools and Vxworks is mediated by a target server and target agent. With Tornado, the cycle between developing an idea and opportunity to observe its implementation is extremely short. Fast incremental downloads of applications code are linked dynamically with the Vxworks operating system and are thus available for symbolic interaction with the minimal delay. A unified macro language called TCL provides a consistent environment for customization across the entire range of graphical Tornado development tools. So we will see in the based upon the Tornado development environment, we'll see initially see cross development with Tornado, and then Vxworks target environment, Tornado host IDE. Within that, we have Tornado editor, project management, like a downloadable application and bootable applications, and steps for creating the downloadable application. Then project, workspace. Then we look at workspace, and then we'll look at bootable application, component tool chain, BSP, that is board support packages. And then after that, we'll go through the compiler, that is CBP, GCC, the C++ compiler, how to do about it, and building an application in it. WCH, that is Wind shell, Wind SH command shell. Then Crosswind debugger, browser, and then WindView software logic analyzer. And then we will go into the Vxworks target simulator, host target interface, and finally we end up with an host target communication configuration. So coming to the cross development with Tornado provides the optimal cross development environment by ensuring the smallest possible difference between the target system during development and after the deployment. So this is accomplished by segregating the vast majority of the development facilities on the host system, while providing precise yet minimally intrusive access to the target. So the hardware in a typical development environment includes one or more network development host system and one or more embedded target system. A number of alternatives exist for connecting the target system to the host, but usually the connection is either an Ethernet or serial link. If hardware or a hardware specific code is not initially available, the integrated Vxworks target simulator can be used to begin application development. So we use a simulator. A typical host development system is fully equipped with large amounts of RAM and disk space, backup media, printers, and other peripherals. In contrast, a typical target system has only the resources required by the real-time application and perhaps some small amount of additional resources for testing and debugging. The target may include no more than a CPU with on-chip RAM and a serial I/O channel, although the connections with the higher throughput are generally desirable. Okay, with Tornado, object module sizes are considerably small during development in contrast with the other environments. This is because there is no requirement to link the application fully. This advantage provides important leverages in cross-development environment. The less data to be downloaded, the shorter the development cycle. The dynamic linking means that it makes sense for even partial completed modules to be downloaded for incremental testing and debugging. The host resident Tornado shell and debugger can be used. You can check in our previous previous block diagram, based upon the block diagram I'm talking about. So the host resident Tornado shell and debugger can then be used interactively to invoke and test either individual application routines or complete tasks. So in addition, the Tornado development environment includes the Crosswind debugger, which allows developers to view and debug applications in original source code, setting breakpoints, single stepping, examining structures, and so on is all done at the source level using a convenient graphical interface. Right. So coming back to the project management. So we have standard text manipulation capabilities, C and C++, syntax, element color, highlighting, debugger integration, and then compiler integration. In that, we'll see the project management. The Tornado project facility simplifies organizing, configuring, and building Vxworks application. It includes graphical configuration of the build environment as well as graphical configuration of Vxworks with dependencies and size analysis. There are several key terms that you must understand before you can use the project facility effectively. First, initially we will understand what is a downloadable application. There are two types of applications. One is downloadable and another one is bootable application. Downloadable application consists of one or more relocatable object modules which can be downloaded and dynamically linked to the Vxworks and then started from the shell or debugger. The IDE is the dynamically loader, the Tornado development environment, which allows objects to be loaded onto running a system. This provides much faster debug cycles compared with having to rebuild and relink the entire OS. A downloadable application can consist of single file containing a single simple hello world routine, or complex application consisting of many files and modules, or partially linked as a single object which is created automatically by the project facility as project name dot out, something like that. So steps for creating it is very simple. To create a downloadable application, you create a project for a downloadable application as shown in this figure, and write your application or use an existing one, add the application files to the project, build the project. See, here we have create a downloadable application, and at the bottom you can see on the top you can see bootable Vxworks image and create new downloadable application, this window. So just click OK and then do all the operations and give a build. So coming back to the bootable application, it consists of an application linked to a Vxworks image, including and excluding components of OS, as well as by resetting operating system parameters can configure the Vxworks image. A bootable application starts when the target is booted. So a project consists of the source code files, build settings, and binaries that are used to create a downloadable application, a custom Vxworks image, or a bootable application. The project facility provides a simple means of defining, modifying, and editing and maintaining a variety of build options for each project. Each project requires its own directory. When you first create a project, you define it as either a downloadable application or bootable application as shown in the figure, right? So in this context, custom configured Vxworks images that are not linked to application code can be considered bootable application. Coming back to the workspace, it's a logical and graphical container for one or more projects as shown in this figure in the right. I think it is not clear. I hope it is clear now. So it provides you with a useful means for working with the related materials, such as associating the downloadable application modules, Vxworks images, and bootable applications that are developed for a given product, or sharing projects among different developers and products, and so on. Example, project name.wpj contains information about the project. Use it for generating the project make files. Workspace name.wsp will show me. This contains information about the workspace, including which projects belong to it. See, workspace allows you to display information about the files, Vxworks components, and build options that make up a project or set of projects shown in above figure. Right? Add, open for editing, compile and delete source code files. See, left corner figure, you can see like you can add, open for editing, compile and delete source code files, downloadable application to the target. So scale and customize Vxworks by adding and deleting components as well as display component dependencies and view object sizes. See the second tab, that is middle one. Look at the figure in the middle one. And for specifying and modifying one or more builds for projects, display detailed build information and modify build options, as you can see in the rightmost corner. So these three tabs comprise of a workspace, okay, default workspace or whatever you say. So a component is a Vxworks facility that can be built okay. A component is a Vxworks facility that can be built into or excluded from a customer version of Vxworks or a bootable application. Many components have parameters that can be reset to suit the needs of the application. For example, various file systems components can be included or excluded Vxworks, and they each include a parameter that defines the maximum number of open files. You can refer the middle figure in these three segments of the figure of the workspace. So toolchain is a set of cross development tools used to build applications for a specific target processor. The tool chains provided with Tornado or based on the GNU preprocessor, compiler, assembler, and linker. However, many third-party tool chains are available. The tool options are exposed to the user through various elements of the project facility. Then talking about a BSP, board support package, consists primarily of the hardware-specific Vxworks code for a particular target board. A BSP includes facilities for hardware initialization, interrupt handling and generation, hardware clock and timer management, mapping of local and bus memory space, and so on. BSPs also include project files that facilitate creation of projects for bootable application and custom Vxworks images. So let's get into the compiler properly. It includes GNU compiler for C and C++ programs, as well as collection of supporting tools that provide a complete development tool chain like CPP, the C processor, GCC, the C and C++ compiler, Make, the program building automation tool, IDE, the programmable static linker, AS, the portable assembler, and binary utilities. These tools are supported commercial versions of the leading edge GNU tools, originally benefit from innovative FSF development, that is free software foundation development environment, as well as for testing and supporting by the Wind River systems. Among other features, Tornado Project Facility provides a GUI for the GNU tools that is powerful and easy. So building an application, to build an application with the default options. So look at this figure, and to build an application with the default application, select the name of the project or any subordinate project object in its folder, and then select build project name.out from the context menu. If you have created the build specification in addition to the default, you can select the build specification you want to use from the build drop down list at the top of the workspace window before you start the build. Note: Tornado only calculates dependencies upon the first use of a file in a build once an initial set of dependencies has been calculated. Tornado doesn't attempt to detect changes in the dependencies that may have resulted from modification of the file. If you have changed dependencies by adding or deleting #include preprocessor directive, you should regenerate dependencies. Any compiler errors or warnings include the name of the file, the line number, and the text of the error or warning text Double clicking on the line containing the error message opens the file in the editor with a context pointer on the offending line. The error or warning text is also displayed in the status bar at the bottom of the main Tornado window. This is about building an application. And then coming on to the WindSH. WindSH is a host resident command shell that provides interactive access from the host to all runtime facilities. And the shell provides a simple but powerful capability. It can interpret and execute almost all C language expressions. It also supports C++, including demangling to allow developers to refer to symbols in the same form as used by the original C++ source code. Thus, the shell can be used to call runtime system functions, call any application function, examine and set application variable, okay, create new variables, examine and modify memory, and even perform general calculations with all C operators. For even more versatile shell scripting and target control, the Tornado shell includes a complete TCL interpreter as well as the C interpreter. Okay, we talked about a macro language called TCL, right? At the beginning. The shell also provides the essential symbolic debugging capabilities, including breakpoints, single stepping, and symbolic disassembler and stack checking. The shell interpreter maintains a command history and permits command line editing. The shell can redirect start input and standard IOs, including input and output to the virtual IO channel supported by the target agent. As a convenience, there is some overlap between WindSH and Crosswind. The Tornado debugger, conversely, the Crosswind debugger provides us access to shell built-in commands. From the shell, you can perform the following debugging, namely display system and task status, generate a symbol disassembly of any loaded module, set breakpoints and single step specific tasks, even set breakpoints and single step the system as a whole, even in interrupt service routines, as with all Tornado tools. So these facilities provide symbolic references whenever possible using the symbol table managed by the target server. So in this figure you can see shell operations involves three components, one of the Tornado system. The shell is where you directly exercise control, okay, on the left. It receives your commands and executes them locally on the host, dispatching requests to the target server for any action involving the symbol table or target resident programs or data. The target server manages the symbol table and then handles all the communication with the remote target, dispatching function calls and sending their results back as needed. The symbol table itself resides entirely on the host, although the addresses it contains refer to the target system. The target agent is the only component that runs on the target. It is a minimal monitor program that mediates access to the target memory and other facilities. So now we can conclude something like shell has a dual role. It can act as a command interpreter that provides access to all Vxworks facilities by allowing you to call any Vxworks routine. It can be used as a prototyping and debugging tool for application developer. You can run application modules interactively by calling any application routine. The shell provides notification of any hardware exceptions. The capabilities of WindSH includes the following: task specific breakpoint. So this is how it appears initially. So the capabilities of WindSH is task specific breakpoint, task specific single stepping, symbolic disassembler, task and system information utilities, ability to call user routines, ability to create and examine variables symbolically, ability to examine and modify memory, and then exception trapping also possible. So we have several task management. So this and all we discussed. So this is how task management. We'll go deeper into it in the next video, like commands like wind sh commands for. We will make a specific video for wind sh commands for task information or for task management and how we can look into it. So we'll straight away skip on to the crosswind debugger now. The remote source, this is the crosswind debugger. The remote source level debugger, crosswind, is an extended version of GNU source level debugger, that is GDB. From your development host, you can use crosswind to do the following. One is spawn and debug task on the target system attached to already running task, whether spawned from your application, from a shell, or from the debugger itself. So use breakpoints and other debugging features at the either the application level or a system level. View your application code as C or C++, source as assembly level code, or in a mixed mode that shows both. So this is the debugging window. So there are several shortcuts like Alt plus 3. You can watch, and Alt plus 4 for variables, Alt plus 5 registers, Alt plus 6 for memory, Alt plus 7 for backtrace. We'll straight away get onto the variables watch. Variables window, you can see that as shows the value of local variables as shown in the figure here. So the contents of variables window always reflect the routine that is currently executing when you step into a different routine. The new routines local variables replace those in the previous display. Then is the registers window. So registers window is just like this. As shown in the figure, the contents of the window depend on the architecture of the target, and the title displayed when that window is not docked includes information about the machine architecture. So when you come about when you want to do a backtrace, then we have got a facility called backtrace window to inspect the calling sequence leading to the current routine. The backtrace window allows you to monitor to the stack. You can double click on the routine in the window to move the context pointer to the stack level in the editor window as shown in this figure. Of course, I did not crop it properly, but just for your understanding. Okay. Then is a memory window that displays a range of target memory starting at the address specified in the starting address control field. The debugger saves each address you type in the field. You can select a previously displayed address from the drop down list associated with this box. To update the memory display, press the button as shown in this figure. No? There is a button here. Okay. So the most favorite part is browser. For my Tornado browser is a system object viewer, a graphical companion to the Tornado shell. The browser provides display facilities to monitor the state of the target system, including the following. One is summaries of active tasks as classified in this figure. The state of particular tasks, including the register usage, priority, and other attributes, comparative CPU usage by the entire collection of the tasks, stack consumption by all tasks, memory allocation, summary of modules linked dynamically into the runtime system, structure of any loaded object module, operating system objects such as semaphores, message queues, memory partitions, and watchdog timers. So we have several browsers. We look one by one, like task list window and task browser. This is how you click here to the browser, then you can see this thing. So we have task list window, task browser, and then semaphore browser and message queue browser and memory partition browser. We'll look into it step by we'll just have a glance at it one after the other, like watchdog browser, etc. So let's get into the task list window. This looks like this, and the tasks in the window are organized into two lists. One is WRS tasks, summary information on all operating system tasks running on the target, and user tasks, that is summary information on all application tasks running on the target. Next is the task browser. To see more detailed information about particular task, use browser task window. The browser displays a window for the task, similar to this figure. In updated version, it would be similar. Okay, I just able to cut only a piece of the older one which is available with me in some of the older documents. At the top of the task browser, you can see global task attributes and information about the stack, allocation, and usage. The last major region shows the hardware registers for the tasks. Their precise organization and contents depend on your task architecture. Next is the semaphore browser. It's a specialized semaphore browser as shown in the figure here. Displays information about the semaphore itself under the heading attributes and complete queue of tasks blocked on that semaphore under the heading blocked tasks. And then POSIX semaphores have a somewhat different collection of attributes, and the browser displays for a POSIX semaphore reflects those differences. Similarly, the semaphore adapts to shared memory semaphores. So you can see here attributes and then blocked and then POSIX. So name, task ID, pre and timeout, all this stuff. Attributes like binary or a FIFO, what sort of queue it is, FIFO here, and pending is 9 and state is empty. So coming to the message queues, to inspect a message queue, by displaying the attributes of the message queue, the message queue browser shows three queues as shown in the figure. So receivers blocked shows all tasks waiting for messages from the message queue, and second one is senders blocked shows all the tasks waiting for space to become available to place a message on the message queue, and then is messages queued shows the address and length of each message currently on the message queue. Shared memory message queues have a very similar display format, differing only in title bar, just as for semaphores. The message queue browser also has a version of POSIX message queue. Then later on we'll move on to the memory partition browser. This is how it appears. Specialized browser windows shows the Vxworks system memory partition, that is MEMSYSPARTIDE. So by default, the memory partition browser displays the following. One is total size of the partition, the number of blocks currently allocated and their total size in bytes, the number of blocks currently free and their total size in bytes, the totals allocated since booting the target system, that is headed cumulatively, the size and address of the each block currently on the free list. So let's move on to the watchdog browser. We have inactive timer and an active timer. Right, before you start a timer, the display resembles the one of the left of the figure, the topmost figure, that is inactive timer. Only the state field is particularly meaningful. However, after the timer starts counting, you can see in active timer figure down, okay, number of ticks remaining, the address of the routines to be executed when the timer expires, and the address of the routines parameters. Then one more is my favorite, kernel class browser. This is how the class browser looks like. Each class has an identifier in the runtime. The symbol names for these identifiers end with string class ID, make them easy to recognize. For example, in this figure shows the display of sem class ID, right? Mm. So you can get a list of class identifiers in your runtime system by executing the following shell window, that is lk-up class ID. If you do this, you get it. Then we will see into the Tornado WinView software logic analyzer for real-time software. We have a WinView here. It is a dynamically visualization tool that provides information about context switches and the events at the that lead to them, as well as information about instrumented objects. Tornado includes an integrated version of WinView designed solely for use the Vxworks target simulator. So what WinView can do for you? Your real-time system consists of Vxworks operating system, your real-time application and the target hardware. The system involves complex interactions among the tasks, interrupts and Vxworks system objects, including message queues and semaphores. These interactions must occur within certain time constraints, often characterized by resolutions of microseconds or finer. While common tools for debugging and benchmarking real-time systems such as source level debuggers and profilers can provide much useful information about a system. They provide only a static picture of a dynamic situation. WinView acts as a logic analyzer for real-time software. It allows you to study the dynamic interactions of all elements of your complex systems. So let's see at color.wvr view graphic here. So you can see on the top we have WinView tool, toolbar docked, and like left you can see interrupts, int0, int3 here. If it is not visible, please kindly listen to me properly, and then all the tasks like t execute task, t log task until the t demo ctr, and then idle loops and time interval. You can calculate time interval, split box, timeline, event tools, state staples, scroll bars. Okay. Problem solution with WinView is because it provides a view into the complex activities of a real-time system. WinView allows you to do the following, namely detect race conditions, deadlocks, CPU starvations and other problems relating a task interaction, determine application responsiveness and performance, see cyclic patterns in the application behavior, save data for deferred analysis, conduct post-mortem analysis of failed system. Throughput in these examples are given to demonstrate configuring and using WinView to solve real life problems. Next is simulator. We'll talk about VxSim, and this is how we get into the VxSim. Is a program that simulates a Vxworks target for use at prototyping and testing environment. The integrated version of simulator allows a single simulator to be run. VxSim optional product adds networking facilities, allowing the simulator to obtain an internet address and communicate with the host or other nodes on the network using the Vxworks networking tools. VxSim is initially a part of Vxworks. In most regards, its compatible or capabilities are identical to a true Vxworks system running on remote target hardware. You can link in an application and rebuild the Vxworks image exactly the same way as in any other Vxworks cross development environment. All Tornado development tools can be used with VxSim. The difference between VxSim and a remote Vxworks target environment is that in VxSim, the image executes on the host machine itself as a host process. There is no emulation of instructions because the code is the host's own CPU architecture. Because target hardware interaction is not possible, device driver development may not be suitable for simulation. However, the Vxworks scheduler is implemented in the VxSim process, maintaining the true tasking interaction with respect to the priorities and preemption. This means that any application that is written in a portable style and with minimal hardware interaction should be portable between VxSim and Vxworks. That means simulator and Vxworks. Okay. So host target interface. The elements of Tornado described in this section provides the link between the host and target development environment. The target agent is scalable component of Vxworks that communicates with the large target server on the host system. The target server connects Tornado tools such as the shell and debugging with the target agent, and the Tornado registry provides access to the target servers and may run on any host on a network. So, target agent represents all the Tornado tools. The target agent is a compact implementation of the core service necessary to respond to the request from the Tornado tools. The agent responds to the request transmitted by the target server and replies the results. These requests include memory transactions, notification services for breakpoints and other target events, virtual IO support, and task control. The agent synthesizes two modes of target control. One is task mode, addressing the task at the application level, and the system mode, system-wide control, including ISR debugging. The agent can execute in either mode and switches between them on demand. This greatly simplifies debugging of any aspect of an embedded application, whether it be a task, an interrupt service routine, or a kernel itself. So the agent is independent of runtime OS, interfacing with the runtime service indirectly so that it can take advantage of kernel features when they are present but without requiring them. The agent's driver interface is also independent of runtime because it avoids the Vxworks IO system. You need to note one point about the first one called target agent is not required. A target server can also connect to the ICE backend, which requires less target memory but does not support task mode debugging. So, as far as Tornado target server is concerned, for example, when a target memory read hits a memory region already cached in the target server, no actual host to target transaction is needed. The target server also allocates target memory from a pool dedicated to the host tools and manages the target symbol table on the host. This permits that server to do most of the work of the dynamic linking address resolution on the host system before downloading a new module to the target. A target server need not be on the same host as the Tornado tools as long as the tools have network access to the host where the target server is running. So target Tornado registry, this is how the Tornado registry looks. Okay, registry, a central target server registry that allows you to select a target server by a convenient name. The registry associates a target server's name with the network address needed to connect with the target server. You can see the registry indirectly through the list of available targets. The Tornado registry need not run on the same host as your tools as long as it is accessible on the network. Excuse me. To help keep server names unique over a network of interacting hosts, target server names have the form target name at host, okay, where target name is the target server name and selected by the user who launches a server with the network name of the target as a default. The registry rejects registration attempts for names that are already in use. It is recommended that a single registry be used at a development site to allow access to all targets on the network. A registry should be should never be killed. Without a registry, a target server cannot be named, and no Tornado tool can connect to a target. So we'll see host target communication configuration. Before that, this is how we already discussed, right? A registry, target server, tools, and target agent, right? Host target communication. This is how the network components are associated in Vxworks. So, but we are interested in target host target communication configuration, right? This is how the configuration. So, host tools such as shell and debugger communicate with the target system through a target server. A target server can be configured with a variety of backends which provides for various modes of communication with the target agent. On the target side, Vxworks can be configured and built with a variety of target agent communication interfaces. Your choice of target server backend and target agent communication interface is based on the mode of communication that you establish between the host and target. Usually it would be network, serial, and so on. No? In any case, the target server must be configured with a backend that matches the target agent interface with which Vxworks has been configured and built. See in this figure for a detailed diagram of host target communication. The default configurations for both Vxworks target agent and Tornado target servers are for a network connection. If you are if you are using a network connection, you can proceed with booting your target. All of the standard target server backends include Tornado connect to the target through the target agent. Thus, in order to understand the features of each backend, you must understand the modes in which the target agent can execute. These modes are called task mode, system mode, and dual mode. Task mode, the agent runs as a Vxworks task. Debugging is performed on a per task basis. You can also isolate the task or tasks of interest without affecting the rest of the target system. In system mode, agent runs externally from Vxworks almost like a roam monitor. This allows you to debug an application as if it and Vxworks were a single thread of execution. In this mode, when the target runtime encounters a breakpoint, Vxworks and the application are stopped and interrupts are locked. One of the biggest advantage of this mode is that you can single step through ISRs, interrupt service routines. On the other hand, it is more difficult to manipulate individual tasks. Another drawback is that this mode is more intrusive. It adds significant interrupt latency to the system because the agent runs with the interrupts locked with it takes control. For example, after a breakpoint, okay. I think if you have already have an development experience, you might be understanding properly what I'm saying. So now we'll speak about a dual mode. Two agents are configured into runtime simultaneously, a task mode agent and a system mode agent. Only one of these agents is active at a time, right? Switching between the two can be controlled from either the Tornado debugger or the shell. In order to support a system mode agent, the target communication path must work in polled mode because the external agent needs to communicate to the host even when the system is suspended. Thus, the choice of communication path can affect what debugging modes are available. I hope we covered almost all of this to the maximum extent of Tornado IDE and related terms. If you really like this video, please subscribe to our channel, give a like, share it. Thank you for watching.